So right now I'm going to walk you through how to do a more complicated quantitative energy problem. In this case, we're going to be solving not just for one answer, but actually two. What this means is occasionally when we have a heating or cooling curve, we're not just going to be solving problems within one region. So if we need to solve in two regions, we'll need to set up two different problems and then either add, subtract, or do other combinations to get two problems together. So for this problem, how much energy must be absorbed by a 150 gram sample of ice at 0 degrees Celsius that melts and then warms to 25 degrees Celsius? What we're going to do for this problem is same thing we do with our LOL diagrams and our more simple quantitative energy problem. We're going to start off by drawing a heating or cooling curve. So I have my blank curve right here. I'm going to read through the problem and find out if this is heating or cooling. How much energy must be absorbed? Hey, absorbed is a key word. That means that it's going to be energy is added to our system. That makes this a heating curve. So it's by a 150 gram sample of ice at 0.0 degrees Celsius that melts. Hey, that's another key word. So if it melts, that means it's going to be a heating curve. We only see melting on heating curves. We see the freezing on cooling curves. And then it warms to 25 degrees Celsius. Okay, well, we know it's going to be a heating curve. Our energy being added to the system on the x-axis, our temperature on the y-axis. So what we're going to do now is we're going to actually draw the curve. So I know we're starting off at 0 degrees Celsius, and then it's going to melt first. We know that melting occurs at 0 degrees Celsius, and it's a flat line. After it has melted entirely from a solid to a liquid, then it can start to increase its temperature. And then that will end up being at 25 degrees Celsius is where the problem ends up. 25 degrees Celsius is where it ends. 0 degrees Celsius is where it starts, and we know that it started off as ice. Well, what this means is we have two regions of the graph. One where it's flat, over here on the left, and then one where it's not flat. What that means is we actually have two regions of our graph, region 1 and region 2. We're going to need to solve for our problem in region 1 and then in region 2 in order to be able to solve for this. But while this is going to take a little bit more time, it shouldn't be too much more complicated. We're going to break this up into those two parts and work on it. What I always like to do is I like to go through my problem with the information that we look for every single time. And I like to use our table that we have in our notes about the different variables that affect heat capacity problems. So every single time we have one of these problems, we're either going to have some form of energy. If there's no energy going into or out of the system, we're not really going to be working with a heat capacity problem. So we're going to have our heat capacity. We'll look for that first. And then we're going to be looking for our mass. Every single problem is going to have mass as well. Now, every single problem is either going to have a change in temperature, if it's a heat capacity problem, or it's just not going to have the change in temperature whatsoever, which tells you it is not a heat capacity problem. And then finally, one thing that every single problem will have, which will vary, is going to either be our heat capacity, our heat of vaporization, or our heat of fusion. Every single problem has one of those three things. So this is going to be the table I use to keep all of my information separate. I'm going to separate that from my values. And then, well, we have two different regions. So I'm going to look for it in region 1, and then I'm going to look for it in region 2. So I'm going to put my information that I know in each of these regions. I'm going to start off just with region 1, this flat region over here. So the very first thing I'm looking for is Q, our energy. Looking through the question, I'm going to see if it tells us any energy that we know. So how much energy? Hey, that's the keyword for energy. I'm going to circle that. Must be absorbed by a 150 gram sample of ice at 0.00 degrees Celsius. That melts and then warms to 25.0 degrees Celsius. Well, 1, that should be a question mark at the end, but 2, it's not telling us how much energy we have. So in region 1, I don't know. I'm probably going to have to solve for that. I'm going to put a question mark now. One thing that I do know, though, is the mass. It tells me that my mass is 150 grams. I'm going to put my 150 grams in my mass column. That's what I have in region 1. Now for my change in temperature. Well, it goes from 0 degrees at the beginning, ends up at 0 degrees at the end. So my change in temperature isn't going to affect this problem. So what that means is I'm not going to be using my heat capacity, C. What I must end up doing is either using my heat of vaporization, which has the keywords evaporation, vaporize, boil, or condense. And that's going from a liquid to gas, gas to liquid. Or I need to use my heat of fusion, which has the keywords melt or freeze, and is when it goes from a solid to liquid, liquid to solid. Well, hey, I see the keyword melt up here. So if I know it melts, that means it's going to be my heat of fusion problem. Now we can look at the table at the top of the page to tell us what the heat of fusion is for water. If we look up there, it should tell us that it's going to be 334 joules per 1 gram. And hey, we have our 4 variables identified for region 1, including the one we're looking for. Energy is what we're looking for in this region. And we have our mass identified, our change in temperature identified, and our heat of fusion identified for this region. What I'm going to do next is I'm going to go through region 2 and see what I can fill in. Once again, looking at the question, I know that I'm still looking for energy, so I'm going to put a question mark there, because that's what I'm still trying to find. For my mass, well, it's not telling me that any of my ice or water is leaving the system. Nothing's entering the system, so it's probably going to be 150 grams still. So I'm going to write that down. Now, for my change in temperature, this is where we actually have a difference. So we're starting off at 0 degrees Celsius in that region, and then we are going up to 25 degrees Celsius. What that means is our change in temperature, how much temperature is changing by, is going to be positive 25 degrees Celsius. So if it's positive 25 degrees Celsius, we now have that filled in. And because this is a non-zero number, what that means is we can use our heat capacity, C, for this problem. Now, at the top of the page, we have 2 heat capacities. One is the heat capacity of solid water, and the other is the heat capacity of liquid water. For this problem, we're going to use the heat capacity of liquid water, because in this region, region 2, it should be a liquid water. The heat capacity there is going to be 4.18 joules are required to change 1 gram of the substance by 1 degree Celsius. So once we have this information filled in for our tables, we can set up both problems in order to solve for those question marks, the things we don't know. So we're going to set up our first ladder for region 1 right over here. But before we do that, we might need to rewrite our heat capacity, heat of vaporization, or heat of fusion in a way that helps us to solve for our, well, answer, which is going to be energy for this problem. So I'm going to write my heat capacity, heat of vaporization, or heat of fusion both ways, because these can be fractions. For region number 1, we're using our heat of fusion, HF, which we can write as 334 joules up on top is the energy required to freeze or melt 1 gram of water. We can also write this the other way, as 1 gram of water requires 334 joules of energy to freeze or melt. Either of these is an acceptable way of writing this, and which way we use it depends on, well, what we're looking for. For this problem, we're going to be looking for energy, which has that unit of joules. So we have these joules either on the top or the bottom. For this problem, because we're trying to solve for joules as our final answer, I am going to use this first fraction right here because it has my joules on top. If I start off with my joules on top, I'm going to end up with my joules on top, and that should give me the answer I am looking for. So at this point, I can now set up the ladder once I've identified the fraction I need. So I'm going to put in the very first value I know, which is going to be this 334 joules on top and my 1 gram on the bottom. Then, well, I'm going to put in the next thing I know. If I go back to my table, I do not know the Q, so I can't put in a Q. I do know my mass, so I'm going to go through and put in my mass. Now, for this problem, we have 334 joules of energy are required to freeze or melt 1 gram. But we have 150 grams. So that means our number should be getting bigger because, well, we have 150 times the mass that is required to change. That requires 334 joules. So I'm going to put my mass up on top with the added benefit of if I have my grams on the bottom and grams on the top, they cancel out. Now I'm going to put a placeholder 1 beneath my 150 grams just because I know we only have one sample that is at 150 grams. So I put that down there just to cancel it out. You do not need to include a unit there. So at this point, my grams are canceled out. The only unit I have left is my joules. So at that point, I should be able to multiply to my final answer. So here, I'm going to multiply everything up on top, which is my 334 joules times my 150, no unit there. What that's going to do is that is going to give me 50,100 joules on top. And then I need to multiply everything on the bottom. This 1 no unit times 1 no unit. So that gives me, well, just 1 on the bottom. Now I need to divide the top by the bottom. That's what the horizontal line is telling me. The 50,100 joules on top is divided by what's on the bottom. Well, 50,100 joules divided by 1 is going to be 50,100 joules. And that's going to be our final answer. And this is going to be the joules of energy that is absorbed in region 1 of our graph. So I'm going to say this is our Q1. Now, I also need to find out how much energy is absorbed by the system in region 2. So I need to do a second problem to solve that. Same thing, I'm going to start off with either my heat capacity, my heat of fusion, or my heat of vaporization, and set up my fraction so that way it's going to be written both ways. 4.18 joules of energy, change 1 gram of the substance by 1 degree Celsius. We can also write 1 gram of the substance changing by 1 degree Celsius requires that 4.18 joules of energy. Now for this problem, we're looking for joules again. And because we're still looking for joules, we want our joules to be on top. So I'm going to be using that first fraction. At this point, I'm going to set up my ladder and write in the values I know. Starting off with that 4.18 joules are required to change 1 gram by 1 degree Celsius. Then I'm just going to go through my table for region 2 and write down what I know. I still know that I have 150 grams. Put that on top, so that way my units cancel out. And we only have 1 of that, so my placeholder 1 on the bottom. But at this point, I actually still have units. I have joules up on the top, and I have degrees Celsius on the bottom. What I need to do now is I need to get rid of that degree Celsius somehow. But hey, for region 2, we actually have our change in temperature increasing by a positive 25 degrees Celsius. So I'm going to put that up on top, and that change only happens once. Setting up this way allows me to cancel out those degrees Celsius, leaving me with just my unit in joules, which is the unit I'll be looking at the end of my problem. So I'm going to put my 2 bars to say I'm ready to multiply across. I'm going to multiply the top. 4.18 times 150 times positive 25. What that's going to do is that is going to give me 15,675 joules of energy up on top, 15,675 joules, and then multiply across the bottom. 1 times 1 times 1 times 1. 1 goes on the bottom, and there won't be any units there. So when I divide the top 15,675 joules by 1, I'm going to get 15,675 joules. Now this is the amount of energy that is going to be absorbed by region 2 of our graph. I'm going to label that as Q2. The question though is not asking us how much energy is absorbed by region 1 or is absorbed by region 2. The question is asking how much energy is absorbed. What we need to do is we need to add together both regions in order to find out the total amount of energy. So